Hello everyone, welcome to chapter 24. It's kind of a hodgepodge chapter in a way, summarizing up and ending a lot of the electromagnetic stuff before we head into light and the properties of light, and then eventually into relativity. So like I said, kind of a hodgepodge chapter. Probably be the last chapter that I do in this format where I have notes and PowerPoint and a picture of me in the background over there, simply because I already recorded a lot of the other, uh, well, really all the rest of the chapters I narrated in the past, and with time restraints, we'll probably just have those narrations for the chapters moving forward, but hopefully they'll be good. And you can always uh, email me questions that you might have. But for this chapter, we're talking more about electromagnetic waves, what they are, and kind of properties of them. Now we've got our review guide, and I'll come back and forth to this review guide every now and then. Maybe move it over just a little bit so you can maybe get everything in there so that you can make sure that you're getting things filled in properly. So I'll come back and forth to back and forth between that image, oops, uh, and the image of the notes, which you'll notice that the notes basically summarize. What I have here is just a summary of some of the stuff that's in the study guide anyway. But let's get started talking about electromagnetic waves. Things that we're going to, you can read over this, just some objectives. What I want you to try and get out of this chapter is to understand the oscillating and orthogonal properties of electromagnetic waves, understand the coexistence of electrical and magnetic fields, accept the transverse nature of electromagnetic waves, that they are not longitudinal, they are transverse. Describe wave-particle duality, meaning that it's that there's particle properties to it as well. It's not all wave. And then we're going to look at how the speed of light, or at least what the speed of light is. We've talked in the past about the calculation of it, uh, such as using rotating mirrors and many of the ways that the speed of light has been measured. So first of all, let's say that I have, and this little squiggly there, remember, means that the tilde means that this is an alternating current. So the current is going back and forth. So I have wires, straight wires connected to the terminals of an AC generator. Since it's AC alternating current, it's going back and forth. Alternating current creates electromagnetic waves. This is a wave of energy propagation. Waves are propagating energy. Now, only the electric wave is shown in this drawing, but you can see that this, if I was to have the flow of electricity, in one moment it's positive one way, negative the other way, and then it switches up. So the current point is, the starting point is the farthest point to the right. The current point is the point to the left here. You can see as the wave moves to the right, the oscillation changes, and when there's neutral, when we're at half of a period, it's back in the node, and then we're at the other direction. And you can see this oscillating nature as the maximum and minimum switch in this wave in terms of the direction of electric movement. And because of that oscillating nature, similar to having something going in a circle, when you have that oscillating nature, you generate a magnetic field. And we've talked before, when you have a magnetic field in a wire, the right-hand rule number 2 tells you that the direction of that magnetic field. You put your thumb in the direction of the velocity and wrap your fingers around. But in these drawings before, what I didn't point out clearly was that it was an alternating current in order for this to work. So at one moment the current is this way, but then at the next moment, the current will be in the opposite direction. It's oscillating, and that means that the magnetic field is also going to be switching back and forth. At this given moment, the magnetic field is going counterclockwise, but when the current switches direction, the magnetic field will be going clockwise. So it oscillates. So let's look at or summarize things that we've learned about electromagnetic waves already, but we just haven't put into a clean package like this. Electromagnetic waves can transfer energy. That's the same for all waves. Electromagnetic waves were first predicted by Maxwell. Electromagnetic waves can move through a vacuum, but they can also move through material objects. Now, it doesn't say that they will move, it says that they can move, because clearly there are some electromagnetic waves. For instance, X-rays don't penetrate lead, so they are absorbed by those materials instead of passing through them or moving through them. They consist of both electric and magnetic components, so it's not just an electric wave and it's not just a magnetic wave. If you have one, you have the other. They can be polarized. We've talked about that before. That's one of the proofs that it is a transverse wave. In a vacuum, all electromagnetic waves travel at the same speed. Now, the key here, and we won't really get back to this until we talk specifically about light, but understand when light hits a medium, this is no longer true. In a vacuum, all light, all electromagnetic waves travel at the same speed, around 3 times 10 to the 8th, or 2.9979 times 10 to the 8th meters per second. But the moment that light hits a medium, it slows down. And then all of the different wavelengths of the energy are they are not going the same speed. They're not all altered by media the same way. And that's why a prism separates the light. It bends. The red light bends differently than the blue light because their speed in the glass prism is not the same. One of them is slowed down more than the other. Even if it's just a small amount, it's enough to separate them because of their differences in speed. But in a vacuum, that doesn't happen because they're all going the same speed. And lastly, we remember that v, velocity, equals frequency times wavelength, and that is a constant for each wave, for each light in a vacuum, because the speed is constant. If I change the frequency in a vacuum, the wavelength changes to balance that out. And then lastly, yep, the electric and magnetic fields are perpendicular. And not only perpendicular, but the right-hand rule, the first right-hand rule tells us that the magnetic field and the movement of the electron and the force are all perpendicular. So it's orthogonal. You have 3 perpendiculars, like the corner of a cube, when you talk about electric field, magnetic field, and force that's exerted upon a particle. So what types of things make an electromagnetic wave? Well, alternating current, or really any oscillating charge. Now, DC current, we usually say, okay, we talk about DC current before, and we had a magnet we were using in one of our labs. We used batteries to generate magnetic fields. But remember, we were moving the magnet. If they were just standing still, there wasn't really an effect. So it was the motion that generated that, and moving it back and forth generated the greatest effect. Because DC current is the result of an electric field, but it doesn't actually produce that field. So in a DC current, we have a difference in potentials, and that causes the flow of electrons in one direction. But that flow of electrons is itself like the electric field tells you what direction that the electrons are going to flow, and that exerts the force upon those particles, because an electric charged particle in an electric field will experience a force, and it's that force that makes the particles move in a DC current. Not super important here, but I just want you to understand that the key is that you need an alternating current. You need something that goes back and forth. An oscillation of some kind is what really does that. And that's why, like in a circular path, if I take a circle and turn it on its side, it looks like I'm going up and down. So a circular path will do that as well. So any charged particle exhibiting simple harmonic motion is really what you get down to. And here's a depiction just so you understand that the electric field and the magnetic field are perpendicular to each other. Now keep in mind though that this drawing is assuming that you have a polarized electric field. But in reality, the electric field is going in every direction at every moment, and it's not necessarily coherent or in sync. So you have like electric fields overlapping, going in every direction, and magnetic fields going in every direction. But for each individual particle that's or oscillation that's generating, for every electric field in this direction, for every E in this direction, there is a B in this direction, and this E and this B will coincide. They will have a relationship. They will be perpendicular, but they're in every direction simultaneously, and because it's not just a single wave, there are many waves moving concurrently. So that's something to keep in mind. They're perpendicular to each other, each individual wave. And then lastly, we already know the speed of an electromagnetic wave in a vacuum is 3 times 10 to the 8th. Now, the fields decrease to zero rapidly as you get farther away. So here's the source. The farther away from this source I get, the less the field strength decreases. But I want you to remember the reason that the field strength decreases is, think about the surface area of a sphere. Here I have a small surface area. As I get farther away, the surface area expands very rapidly, and it expands faster by a squared factor, faster than the surface area expands faster than the radius because of the way you calculate the surface area of a sphere. So because of that, as you increase the distance, you quickly lose the magnitude of that electric and magnetic field. Now, together, these electromagnetic fields are called the near field when they're close together. The farther away, as it converts from a direct causality of electromagnetic waves, as you get farther away, it becomes you get this induced field. And we call that the radiation field. So I guess for now, because I really need in class and drawings to really explain it, but you have a near field, which is when you are close, and the far field is the radiation field. Close up, we call it a near field, and it's much stronger, I guess, is what you really want to understand. And both of these are moving along. The wave itself is moving as a transverse wave, and they are perpendicular to each other, and it can move through a vacuum. I just keep throwing review stuff on there as we go. Now, let's say that I have a radio wave, and this particular instance of the wave, this one part of the wave, is going up and down. If I have an antenna oriented that is parallel, so here's my parallel field, my field and my antenna are parallel. As this electric field hits the antenna, it will cause a current to begin to exist in this wire. So what you get is you get a current that goes through here. It goes through this coil, which generates a magnetic field. That magnetic field transfers over to the other coil, which converts that back into an electric current, and that current then runs through the wire to audio, video, or some other kind of circuits. But the neat thing about this, and why I put it up here, is you can see that a wave traveling through space interacts with the antenna, which generates a current, and that current generates a magnetic field, which then creates another current. And this allows you to basically transfer, and you can use capacitors to control the flow. There's a lot more to this, but I just want you to understand that for radio waves, you want the antenna is only going to pick up the maximum amplitude of a wave that is parallel to it. If a wave is completely perpendicular to it, it gets 0% of the field because it's only velocity in the correct direction that matters. And anything that's at another angle, it's only the parallel component that matters. Now here, for every vertical electric field, there is a horizontal magnetic field. And with a receiving antenna in the form of a loop, it's actually the magnetic field that's detected. And notice how the loop is in the same orientation as the electric field, but the loop isn't picking up the electric field, the loop is picking up the magnetic field, right? And because the magnetic field in the loop will be through the loop, an alternating current where you have an oscillating magnetic field, it will be able to detect that and generate the same kind of a magnetic field, creates an electric current, current creates magnetic field creates a current. So they're very easy to interchange. Now, the frequency of an electromagnetic wave we've talked about a lot, F. And what that is determined by, what actually determines the oscillation frequency of most electromagnetic waves is uh, the oscillation frequency of the electric charge at the source. So here's an electric particle, positive or negative, doesn't matter, and it's vibrating at a certain frequency. That frequency, the source, is what determines the frequency of an electromagnetic wave. So that's the key. And we've talked about that before, like with the Doppler effect and other things, how it's the source that determines the frequency. And that's still true with electromagnetic waves. Now let me just real quickly switch back over to my notes here so that I can show you. We should be pretty far along in here. But I want to real quickly before I move on with the, well, actually, no, I want to finish the electromagnetic spectrum. I'll come back. Like all waves, electromagnetic waves have a wavelength and a frequency within the electromagnetic spectrum. And there's the electromagnetic spectrum is huge here. We see from gamma rays all the way up to AM waves, and they continue to get larger from there. The visible wavelengths are a very small portion of that, where infrared and ultraviolet are on the outside. So this is the electromagnetic spectrum, and it relates. If you look at the top, you see the frequency, and the bottom, you see the wavelength. As the frequency gets bigger, the wavelength gets smaller. As the frequency gets smaller, the wavelength gets bigger. And there's actually a point at 10 to the fourth, around 10 to the fourth, where they are about the same, because when you multiply them together, I get 3 times 10 to the 8th. So the square root of 3 times 10 to the fourth is where the frequency and the wavelength are the same for light. So let's look at an example of how do we use this C equals F lambda equation, which we've used before. Speed is equal to frequency times wavelength, so wavelength has to equal speed over frequency. Find the range in wavelengths for visible light in the frequency range between 4 times 10 to the 14th hertz and 7.9 times 10 to the 14th hertz. Well, first I calculate the wavelength at 4 times 10 to the 14th, then I do the same thing at 7.9 times 10 to the 14th, and I get 750 nanometers and 380 nanometers, and then I would just, so that's the range from 750 to 380. And if I go back here, and it's nanometers, so that's times 10 to the 9th. And so we can go in here and we can say, okay, we're at 10 to the 9th. We're talking about, wavelengths in the, 10 to the negative 7th range. So I can look here, it's hard to go back and forth. I look at the wavelengths in the 10 to the negative 7th range, and where am I? I'm kind of right in the ultraviolet range. So that'd be like the 10 to the negative 7th range. But 3 times 10 to the negative 7th would be in this color range at the top of the violet. So we're basically going from violet to ultraviolet there. Point is, I think you guys can all do speed equals frequency times lambda equations. Let's look at a conceptual example, the diffraction of AM and FM radio waves. Diffraction, if you remember, is the ability of a wave to bend. Actually, if it's not refraction and it's not reflection or absorption, so you have absorption, reflection, refraction. If it's none of those, it's diffraction. Everything else is defined as diffraction. And part of diffraction is the ability of a wave to bend around an obstacle at the edges of an opening, right? So we showed pictures of that before. Now, understanding that, and remember that with diffraction, if the opening is the same size as the wavelength, you get, or nearly the same size, a little smaller. If the opening is a little smaller, you get the most diffraction. So which one would you expect, AM or FM radio waves, to bend more readily around an obstacle? Well, the larger the wavelength, the more likely it will be that a single wave will interact with an edge. So the answer is, and we've talked about this before, the larger, back in 17.3, we learned that a greater wavelength gives a greater diffraction. So AM has a greater wavelength. And that's where you just need to start to know this electromagnetic spectrum. AM has a small frequency, large wavelength. Gamma has a very high frequency, very low wavelength, and frequency is also directly related to energy, so gamma rays have a very high energy. And of course, I've got a picture here of kind of one of the original experiments for determining the speed of light, where you had a rotating octagonal mirror, and the fixed mirror was, yeah, like 30, I don't know if that was 35 or 3.5 kilometers. I think it was 3.5 kilometers, but I know it's been done with different distances. Now I can't remember the actual, I mean, so the mirror was on a mountain, and then you had the oscillator. I can't remember the exact distance, but with experiments like this, you can measure the speed that the mirror is rotating. And if you know how far, so in this case, this light has gone 70 kilometers because you want it to be a long distance to get an accurate reading, you can measure how long it takes this to spin would equal the time it takes the light to go 35 kilometers. So you have a distance and you have a time, and you divide and you get speed. Let's look at some concepts, and then I think I'll be done with this video. A supernova is a violent explosion that occurs at the death of certain stars. The figure shows a photograph of the sky before and after a supernova. Why do astronomers say that viewing of an event like this is like looking back in time? Well, the reason is, and this is in your book, because that particular supernova is 1.66 times 10 to the 21 meters away. So distance divided by speed tells me that it took 5.5 times 10 to the 12th seconds. So that light, that event happened that many seconds ago. It's looking back in time. Now we talked about Maxwell being one of the first. The electromagnetic wave properties were first predicted by Maxwell. He actually had this prediction that the speed of light would be 1 over the magnetic times the electric permeability of free space, square root of their product. So taking into account both the electric permittivity and magnetic permeability, since it has properties of both, multiplying them together, taking the square root, is kind of like a fancy way of averaging out two numbers. 1 over that average is the speed of light. It turns out to be true, that these two things, that the speed is related to both magnetism and electric permittivity. So that's more just to tell you how that these two things are related. So like I said, this first section is kind of a hodgepodge of a lot of stuff that we've already learned. And it may have seemed like I was going all over the place, and that's because this section of the chapter really does go all over the place. In the next video, we're just going to talk specifically about energy being carried by these waves. Okay. Now I've in terms of the review guide, we've gone through pretty much the entire front page. If you want to kind of pause it, you can get some of the answers that you might be missing from the study guide at this point, and look at some of the self-tests and how they're done. And when we come back, I believe that this sunlight entering example is one of the next examples. So that's kind of where we are. So that's it for now, and I'll start the next video.